Derivatives number 9 will be a continuation of our motion topic. We're going to talk about average velocity and how that differs from instantaneous velocity. We're also going to talk a little bit about speed, how to tell if speed is increasing or decreasing, and also what you need to do to sufficiently justify your answer for that. Let's talk about average velocity versus instantaneous velocity, and I'm going to give you a quick little example that will demonstrate the difference between the two so you understand exactly what we're doing with that. So let's say that you went on a trip and it was 200 miles long and it took you 4 hours to cover those 200 miles. If you did a simple D equals RT formula, that will give you 50 miles per hour. So what that means is you averaged 50 miles per hour over that 4-hour time interval. It doesn't mean that you went 50 miles per hour during those 4 hours. It just means that that was your average. So sometimes you might have gone faster, sometimes you might have gone slower, and just the average ended up being 50 miles per hour. So that's the question that you're answering when you do an average velocity. You're doing in velocity over an interval of time, and it is just an average. On the other hand, when you do instantaneous velocity, you are saying what your velocity is at a moment in time. So just back to our trip over here, the question I'd be answering with my instantaneous velocity is how fast were you going 2 hours and 42 minutes into a trip? So just for example, 2 hours and 42 minutes into the trip, what was your velocity at that particular moment in time? As you see, we're answering two different questions when we're answering that average velocity versus instantaneous velocity question, and we may or we may not get the same answer for each one. Our average velocity is going to be a slope of a secant line, and we've talked about that one before. I'll give you a neat way of thinking about this. Think of velocity in terms of how we defined velocity. We define velocity as the rate of change of position. So if I substitute this word velocity with rate of change of position, I have now turned this into an average rate of change problem. And we talked about that at the beginning of the derivatives unit. An average rate of change is just f of b minus f of a over b minus a. But since we're doing an average rate of change of position, every place I just said f, you're going to substitute in that position function, which we're calling x. So my average rate of change of position is going to be x of b minus x of a over b minus a. So it's just your change in position, so how your position changes, we call that displacement, over how your time changes. So another way of looking at this is delta x over delta t. So change in position over change in time. Notice there were no derivatives taken in this, and if you look at the units on this, it matches up because my position is a linear measurement, so I would have something like meters. Time, a measurement of time would be something like seconds, and when I do that calculation, I end up with a unit that says meters per second, and I know that to be a velocity unit. Our instantaneous velocity is velocity at a moment in time, and that was our slope of the tangent line, which you know to be our derivative. So my v of t, my instantaneous velocity, is just the derivative of my position function, so x prime of t. Next up, we're going to talk about speed, and we had defined speed previously as being the absolute value of velocity, and you know that an absolute value just takes positive values and keeps them positive, and it takes negative values and turns them positive, just does the opposite of those. So if I want to do the absolute value of velocity, I've got a sample velocity graph over here, and I'm going to do exactly what I have written in red over here. The parts of this graph that are positive are going to stay positive. So this portion of the graph is positive, meaning above the x-axis, so it's going to stay positive. Any parts that are negative, so down here, these negative parts of my velocity, are going to turn positive. So I'm going to reflect them over the x-axis, and it'll look something like this. So my speed graph actually looks like this, the red one that I have graphed. So that one is speed. And I can see that speed graph is increasing. So if I want to know where speed is increasing, I look literally where this graph is increasing, and I see two intervals of increase on that speed graph. What I want to do is relate them to that velocity graph. So instead of looking at the speed graph, I'm going to look at the corresponding interval on the velocity graph before I reflected it. So what we're going to want to be able to do is to relate these intervals of increasing speed to this velocity graph. So we're going to hide the speed portion from our view, and I have in green the intervals that we're interested in, and we're going to pay attention to what's going on with these two intervals. So when I look at this one, what I see is that my velocity is positive. That is, we are above the x-axis. And also at the same time, if I look at acceleration, because my velocity is increasing on this interval right here that I've identified as increasing speed, I also have a positive acceleration. So in this interval of increasing speed, my velocity is positive because I'm above the x-axis, and my acceleration is positive because my velocity is increasing. Let me take a look at my other identified interval of increasing speed, which is down here. And what I see down here is that my velocity is negative. That is, my velocity graph dips below the x-axis. And on that same interval, my acceleration is also negative because my velocity graph is decreasing. Another way of looking at this is you will know that your speed is increasing if your velocity and your acceleration are both positive, or if your velocity and acceleration are both negative. In other words, if your velocity and acceleration have the same sign, then I will know that I'm dealing with an interval of increasing speed. So let's look at decreasing speed. Again, I'm going to take a look at this speed graph and look for where that speed graph is decreasing. And I can see my speed is decreasing here and again here. And I want to relate those to places on the velocity graph. And my velocity graph was this one that dipped below the x-axis. So I can see that the corresponding interval would be this one. So now I want to pay attention to those intervals I have identified on the velocity graph. So analyzing these intervals like I did the increasing ones, I can see this interval of decreasing speed. I have a positive velocity because I'm above the x-axis, but my acceleration is negative because my velocity is decreasing. If I look at my other interval that I have identified as a decreasing speed, it's this green one right here, and on this interval my velocity is negative because my velocity graph is below the x-axis. And looking at my acceleration on that same interval, I see my acceleration is positive because my velocity is increasing. On these intervals of decreasing speed, what I see in my relationship between velocity and acceleration is I have a positive velocity with a negative acceleration, or I have a negative velocity with a positive acceleration. In other words, my velocity and acceleration are going to have opposite signs. This is a really popular kind of question that is asked on the AP exam, and I've given you a little AP exam tip right here. The reasoning that you want to use if you're asked a question about increasing or decreasing speed is exactly what we laid out right here. So just refer to velocity and acceleration and compare their signs. If they have the same sign, we're going to say speed is increasing. And if they have opposite signs, we're going to say our speed is decreasing. On the back, we've got a few examples. It starts off with a review of our first motion section. So part A wants to know how many times does our object change direction? And this is a velocity graph. And I know I'm looking for where my velocity equals 0. And we equal 0 in 3 places. But I only undergo a sign change in 2 of those. So here and here. So my answer is 2 times. And my justification is just what I was looking for in that graph. That is velocity equals 0 and change of sign. The next question is asking for where is acceleration positive. And I know acceleration is positive where my velocity is increasing. Again, this is a review of what we did previously. And I have 2 of those intervals. So from 2 to 5, 7 to 9, and my reason is because velocity is increasing. My next question is a new one, and it's asking me at t equals 2.5, is speed increasing or decreasing? And I need to justify my answer. So I first go and I look at 2.5. I'm about right here on the graph. And what I want to look at is make a relationship between the velocity and acceleration at that point. And what I see is at this point of 2.5, my velocity is negative because I'm below the x-axis, but my acceleration is positive because velocity is increasing. And what we said previously was if velocity and acceleration are opposite in sign, that means that we have an interval of decreasing speed. And my reasoning is just what we said on the front. My speed is decreasing because velocity and acceleration have opposite signs at my point in question at 2.5. On a question like this, you're going to want to lay it out exactly like this. Do not just write this statement out. Give a little bit of evidence, which is what this is. I'm giving some specific information about this question over here, and then I'm just summarizing it in this statement. In question 2 down here, I'm doing this analytically as opposed to graphically, and I'm given a position equation here. And my first question wants average velocity. And keep in mind, average velocity actually has nothing to do with the derivative. An average velocity is just change in position over change in time. So I'm going to take an approach of an average rate of change on this time interval. So that's my A and my B. So I'm going to do x of 2 minus x of 0 over 2 minus 0. And now I just plug into my position function and calculate this. And so I get this -8. If I had units in this problem, let's say our distance was measured in meters and our time was measured in seconds, then my unit on this would be meters per second. So my average velocity is -8 meters per second. The next question is an instantaneous velocity. So when you see instantaneous velocity, that is velocity at a moment in time, and that's what the derivative does. So I'm going to do the derivative of our position. On a question like this, I'm going to want to show that derivative in terms of t, and then evaluate at my t value of 1. And I get my instantaneous velocity at t equals 1 is -9 meters per second. The last question is on increasing and decreasing speed at t equals 1. And again, I'm going to refer to the relationship between velocity and acceleration at my time in question. So first I'm going to find my velocity at 1, which actually I've already found in the previous question. I need to find my acceleration at 1, so I'm going to have to show that acceleration function first and then plug a 1 into it. And when I do that, I get my acceleration at 1 is a -6, my velocity at 1 is a -9, and because they are both negative, they both have the same sign, I know that my speed would be increasing because they have the same sign. And so I just summarize that in a statement like this. Make sure when you do these increasing or decreasing speed questions, you don't just lay out a definition. Give some information that's pertinent to the exact question at hand. So you want to be into this problem and give specific information about this problem.